Okay, let's get started. So, are there any questions? Yeah.
When we're studying for the test on Tuesday, are there any specific concepts or problems that you think we should be focusing on?
So, you actually bring up a good point. So, what is the test going to actually cover? I didn't give a straight answer yesterday, but here's the straight answer. It's what we covered in Chapter 2 and all of Chapter 3, which we're going to finish today. So basically everything in Chapter 2 except for the deterministic context-free language stuff is interesting, but it's a little complicated and we don't want to get into it too much. But everything on Chapter 3 in addition to that. And then we may start Chapter 4 a little bit today, so Chapter 4 will not be on the test at all. So, but for studying, I ignored your question entirely. So, what was your question? Like study habits or what?
Yeah, like just like any tips, I guess, for some of these tests.
Yeah, so it's basically the same idea, the same format as the previous test. So 5 questions and a bonus one. So focus, what are the main things? So can you enumerate some of the main things that you might possibly see? So grammars, but like what related to grammars? What did we do with grammars? Yeah, well, PDAs, but what did we do? Did we just talk about CFGs and just make CFGs all day, or what did we do with them? Oh yeah, we converted to CNF. So we converted a grammar to CNF. What else did we do? Convert a CFG to PDA. And what do you think else? Someone said it, I think. CFG to PDA. PDA is CFG. We always have to have a round trip when we're flying, right? We got to return home. So CFG to PDA, PDA to CFG. That's a good example because it's like airport names, but anyway. So those types of things. What else might you see?
Turing machines.
Yeah, Turing machines because we're doing Chapter 3, so Turing machines, of course. And whatever we're going to get to today, of course. What else? Pumping lemma. Does that sound like 5 questions? It's not going to be that, but it's to get you to think about what types of things are important. I'm not going to ask you straight, convert this CFG to a PDA directly. That's not going to be the exact question I ask. I may ask you, what if we had a grammar that is guaranteed to be in this form, not necessarily in CNF? Can we skip some steps to go to CNF? So like if we know that the right-hand side of every rule is at most 2 in length, can we skip a step when we convert to CNF? Yeah, because one of the steps in the CNF conversion is removing long right-hand sides of length at least 3. But if every length is at most 2, we can skip that step. So it's thinking about that sort of thing. I may possibly ask you to do the actual conversion, kind of like what we did on the first midterm, but it's not going to be just straight up do this conversion, do this, because I'm not testing if you're a computer. I'm testing if you understand the concept, okay? Does that make sense? Okay. Other questions?
Could you do the 0 to the n, 1 to the n, 2 to the n example for the Turing machines?
Okay. Yeah, sure. So, do you guys want to see a Turing machine diagram example? Okay. 4 people nodded their heads because those are the people who are awake. I'm kidding. Let's actually do an example. So, is this language context-free? No. So, we can't make a CFG for it or a PDA. So, I want to make a Turing machine for it. So, let's break out our sample tape right here, and let's just say we have the zeros here, ones here, and twos here. Whenever you do problems like these, after you do some of them, you kind of get a feel for how you should approach them. But when you're starting out, what I would recommend is making an actual tape like this with a single example and try to think like, how would you figure out whether the number of zeros, ones, and twos in this is exactly the same? So what would you do here? Well, we actually kind of outlined the strategy way early on. Yeah, so there's a problem with this. We'll fix it later. To mark off the first, I'm going to use a different color. I'm going to mark off a 0. Then I'm going to keep going right until I mark off the first unmarked 1. And then I mark off a 2. And then when I'm done marking off the first 2, that's unmarked, then I come back and then I go through again over and over. So I go through marking 1, 0, 1, 1, and 1, 2 off, and then when I do that, I go back to the front, and then I make another pass, make another pass, make another pass. And how do I know that I'm done making passes? Well, if there's nothing left to mark, what should I see along the whole way? Just X's. So if I see a bunch of X's and then I hit a blank at some point, then because we didn't make any blanks at any other point, we have exhausted the whole input and we were okay every step of the way, so we're okay here. Okay, great. So the problem that we have seen, we've seen this before. The problem is that at the beginning, how do I know when to stop moving left? So there's actually an easy way to do this. We can do it with an X. Why can we do it with an X in this case? Here's why. Suppose that we mark this 2 right here, and we're destined to go backward. Well, what do? We see an X right here. As long as we're seeing X's, move left. And then what will I see next? Ones possibly. So then I traverse past the 1s. Then what do I see? X's, then I see zeros, and then I stop when I hit an X. So if I hit an X after I see a 0, I'm done moving left. So in here we didn't need to put a special character, a different character at the front. We could just deal with X's here. Yeah. No, you can put a special character here. So remember, all these problems can have infinitely many ways of approaching it. There's no necessarily wrong or right way. They're just multiple ways. So let's take this approach. Actually, let's take your approach because it'll actually make the diagram slightly easier and smaller. And I think we're all in favor of that. So in this case, let's put a $sign, a different special symbol just at the front. And then when we make passes through after that, we're going to put X's all the way through. Because why would we do this? Because here, when we're done marking the 2, we just keep moving left no matter what we see until we see the $sign. We don't care what we see along the way. So I think that'll make things a lot easier. So let's make a machine for this. So we have to start with a start state Q0. And if I see, so let's do the very trivial case first. What if I see a blank as my symbol? I should accept. Why? Yeah, so if I set n to be 0, that's the empty string, which is, I see the blank as the first character. So if I see a blank, we might as well just move right and then go to Q accept. So that's pretty easy. Cool. So the only other case then that we need is we see a 0 first. So whenever you're making these diagrams, think about the path that will get you to accept. don't think about the things that can go wrong. Think about the things that can go right. So could we see a 1 or a 2 as the first character? No, we could see it as the first character because we're just presented an input with 0s, 1s, and 2s in it in any order. We're to figure out if it's 0, 1, 2 in that order. But a 1 or 2 could appear first. And in fact, if we're putting X's and dollar signs on the tape, we could see a dollar sign or an X as the first character the first time. We know we won't, but it's just possible that it could, per the definition. So we could think about all those possibilities. We know they all go to Q reject, but let's not think about them and then just say all the other transitions go to Q reject at the end. So the only thing we really care about is a 0 at the front. So if we see a 0, then we're going to change it. We're going to change it to a dollar sign and move right. And I'm going to call that next state Q1. So what will we see after this dollar sign? What could we see along the way before we get to the ones part? So this is at the very beginning. Yeah, just zeros. So here, am I going to change any of those zeros along the way? No, because we're only marking 1, 0, 1, 1, and 1, 2 at a time. So in Q1, we're just going to skip past the zeros, essentially. As long as we're seeing zeros, just move right past them. Even though we really are writing a 0 there, we can just think of it as skipping it. And then what will we see after that? 1. And what do we want to do with that single 1? Change it to an X. Cool. So we're going to change the 1 to an X and, of course, move right. Let's go to a state Q2. So we're going to make a transition here, and we're going to augment it later. So what will we see after we mark that 1? What will we see afterwards? A bunch of 1s. It's actually, we're going to see X's too, but let's just do the 1s first, and then change our thing later. So as long as we're seeing 1s move right, then what will we see after that? A 2, and what do we want to do with the 2? Change it to an X. Cool. And move right. Actually, should we move right? I mean, we could, but it's kind of a waste of time. So let's move left. It actually won't make a difference here. Because to get to this point, we've had to see 2 characters anyway, so moving left is there's no problem with that. Okay, so now we're moving left. We've made 1 pass through the input. Now what are we going to do? Yeah, move all the way to the front. And when do we stop? The dollar sign at the front. So what are we going to possibly see along the way? Well, we may see X's, we may see 1s, we may see 0s, and maybe 2s. We won't actually see 2s, but let's just say all of those are possible. So here, we're going to move left if we see a 0. We're going to move left if we see a 1. We're going to move left if we see a 2. We're going to move left if we see an X. And those are the only other things. Oh, we should say if we see a blank for whatever reason, we should move left too, but we're not actually going to see those, yeah.
Should we move right to see all the clues so that it was kind of...
Oh, okay, yeah. You're right. That's my mistake. There's actually something wrong with going left here. And the reason is, so good thing you brought that up, is the input 0, 1, 2, just the single one of each, then I need to be able to move right. Well, if I moved right here, then if I did everything correctly, I will see a blank on that particular input, 0, 1, 2. If I marked the 0, 1, then the 2 and moved right, then I should see a blank symbol. So here, if I see a blank symbol, I should accept. Thank you for bringing that up. Okay, so we should actually move right here.
What
Yeah.
if we did it all the way to the back, but then we go through again, we see it blank, then we can answer.
We'll handle that case. We're not quite there yet. So we're not done with the machine yet. So we gotta move left. So in Q3, we're going to move left. So if we see a, let's see, yeah, so if we see a 2, we should move left. If we see a 1, we move left. If we see a 0, move left. And we see an X, move left. So if we see a blank, yeah, go ahead.
If you see a blank, what if it was 0, 0, 0, 1, 1, 1, just a single 2, which is right? You'd see a blank, that'd be incorrect.
Oh yeah, good point.
So, if we did-
That's the problem of doing an example live. Yeah.
so can we do it from Q2 to Q3, move left instead of right?
Yeah, the problem is that we're, there's no spacing between the inputs. Let's see.
You can, if it's correct, when you go through it the last time, it'll be all
Yeah, that's what I'm thinking.
Yeah.
Yeah, so I think this is fine. The last time through, yeah, you're right. We should just see X's along the way. So if we're moving left, the thing that we will eventually see is the $sign, and we move right. But what state should we go to here? Well, let's see. If we have things that are partially marked X's along the way, then we should move past those to find the first unmarked. Yeah, so here, if we go to here, then we're at the very front, then we have something of the first set of zeros that are marked with X. So we should move past those to find the first unmarked 0. So we're just going to skip past those. And then if we see a 0, then we're going to go back to Q1, because Q1's job was when we get to Q1, we have marked a 0 somewhere. So here, we're going to have Q0 goes to X and right. Yeah, that should be fine. So the only thing that could go wrong then is in Q4, we see X's, and then we eventually hit the blank symbol, which means that we should accept at that point. So here we should go to accept. Thank you for the correction. I'm confident this is right now. So let's review what the Turing machine is doing. The very first transition, not the blank one, the 0, 1, is marking that special symbol on the front. Then we're skipping past all the zeros. Yeah, because the very first time, we're going to see just zeros on the tape. Then we get to 1. Then we skip past all the 1s. Then we get to 2. Mark a single 2, then go back. The problem is when we get to the Q2 self loop. Well, what could happen is we mark a single. Yeah. So when we get to when we mark the single 1 here, I should rephrase and not speak so quickly. So when we mark the first unmarked 0, we're going to see some zeros. And then at some point, we're going to see X's. And after that, we find the 1 that we want to mark. So here on Q1's self loop, we better add a X goes to right here, because that corresponds to moving past the zeros that are not marked yet, and then the X's, which are the ones we've already marked. And then we skip past those to find the 1 that is not marked yet. So then for that same reason, on Q2 self loop, I'm going to add an X goes to right also. Because when we mark a 1, we have some 1s that are unmarked so far. And then after that, we have some 2s that are already marked, so we got to skip past those to find the next 2 that is not marked yet with an X. But everything else follows through because we mark a 2, then skip all the way back to the front, we find the $sign, move right. Once we move right, then we're at the beginning now where the first marked thing is. Then we skip past the X's at the front, which is the marked zeros. And then we eventually, hopefully, find the first unmarked 0. And then we proceed through another iteration. Otherwise, the entire tape now is all X's. And then we find a blank at the end, which means that we were OK all the way through. And then, therefore, we should accept. Does that make a little bit of sense? Yeah.
Are we missing a blank for this over in Q3?
Technically, yes. The thing is, we won't have to worry about that because we're not writing any blanks intermediate. But you're right. If we want this to be a deterministic machine, then we want to do something on every possible value that we can see. So what we could do is say, we would never encounter that transition anyway because we're never writing a blank halfway through. But if we somehow found it for whatever reason, then we can just say, oh, that's not expected behavior to go to Q reject.
No, I mean for Q3.
Yeah,
So-
for Q3. Mhm.
So if we read 2, or it's 0, 1, 2, just 0, 1, 2. The next one is going to be blank. So
That's fine. So let's look at the 0, 1, 2 example. Oops. So if we have 0, 1, 2, then we're going to mark $sign on the front. Then we're going to go to Q1, then go to Q2, mark an X. Then we go to Q3, and Q3 says go back to the front. And then that means that we're now at the $sign, move right. Then Q4 self loop says move past the X's, but then now we hit a blank. And so you're right. If we hit the blank immediately, it seems like we should accept, right? The problem with that is in this example. What if we had 2 zeros, a single 1, and a 2? Then on our first pass, we're going to mark the 2 and then hit the blank, but we still have a 0 left. So we need to go back and make another pass.
You just
Okay.
need to add it to the loop of the Q.
Yeah.
0, 1, 2, X loop is what you need to add it to.
Oh, I see. Yes, you're right. Yeah, thank you. Yeah, and then, of course, all unwritten transitions go to Q reject. See, it's so simple. Yeah, so this was a little harder because, and I thought it would be easier, by putting all of the Q3 self loops together, so we didn't have to worry about like where we actually were in the input. It actually turns out to be a little harder because now we have to reason about, are we hitting the end of the input, and now we got to manage the $sign symbol at the front. So it's a little more work. If we wanted to do like 0 to the n, 1 to the 2n, and 2 to the 3n, so we would augment these transitions to say instead of 1 goes to x, comma r, we would have 2 transitions of that form, and for the 2 transition we have 3 of them. Yeah.
Outside of like thinking about paths to accept, like how do you know you're developing a test cases in order to overall solution?
So if it's of a input that you know will not accept, you don't need to worry about those, because at some point it's going to be one of the transitions you didn't define, which go to Q reject anyway. So you just need to think about the strings in the language and then think about what their structure is. Well, the structure here is just a bunch of zeros, then ones, then twos. Then you just look for the first unmarked 0 and the first unmarked 1, first unmarked 2. Other questions? Yeah.
The first question on it says show that if L is the CFL and R is the regular language, then L intersect R is also the CFL.
So this is what the question asks, essentially. Did anyone do this question? So, what do you think I should, what you should do after this? Yeah, do it. So, how would you prove this? Well, suppose that L is not a CFL, but is regular. If L is regular and we want to show that L intersect R is a regular language, how would you do that? Yeah, to do product construction and with intersection. So could we try something here? It might not work. Let's try. So if L is a CFL, what is the machine model for CFLs? PDA. So L has a PDA. And R is regular, so it has what? Yeah, R has a DFA. What does a DFA not have that a PDA does have? A stack, right? So could we think of a DFA as a PDA that does nothing with its stack? Yeah, this is the same idea. So let's think about this. Could we try doing a product type construction here? Where we just take the product of the states and then just figure out where the PDA would have gone and figure out where the DFA would have gone and then merge them in the product thing. Well, we gotta be careful here because the PDA has a stack. So the product thing that we're trying to make for the context-free languages, it probably is going to be a PDA. So it must do something with its stack. So if we have a transition from like Q to Q prime in the PDA of the form, let's just say A, B, C. So it pops B and pushes C. And then in the DFA, we have reading some input D. Well, what would we do in the product thing? So remember, for product, we are taking the Cartesian product of the states and then figuring out where we can go. So in the product PDA, we'll have these ordered pairs of states. So in this particular case, we'll have a transition from QR to Q prime R prime. Oh, well, actually, let's just say that they read the same thing. They have to read the same thing because in the product construction, we look at where they go on the same character. So what would the transition be in this case? Well, think of the DFA as a PDA that ignores its stack. So if we're building a product PDA here, then the PDA that we're building should do the same stack operations as the original PDA did, because the DFA is going to not do anything. It's not going to muck up the stack. So for the product PDA, we should do the exact same transition. Okay, so it's basically doing the stack operation of what a PDA would have done. And in fact, if the PDA did nothing with its stack, so it's just a DFA, we recover the original product construction. Why? Because if the PDA here, the original one, had nothing to do with its stack, then both of the stack operations would be empty. So that means that the product PDA would be doing nothing with its stack either. So that means that the product PDA really is a DFA. So we really do get the original product construction this way. So by doing this, we're mimicking what the original machines would have done, as well as what the stack would have happened in the original PDA. So in fact, we can easily do it this way. There's another way to do it with context-free grammars, but it's a little more complicated. But any questions about that? The high level is better than this here.
Is it regular? Is that intersection?
No. So we're building a product PDA because we have to do something with the stack. So in general, it's a context-free language. It may be regular, but it's always a context-free language because we're making a PDA for it. Yeah?
So does this mean that context-free languages are closed under intersection?
Intersection with regular.
Well, because, I mean, it's just a type of context-free language.
Ah, so this is a red herring. So does this imply that the context-free languages are closed under intersection? No. It shows that they're closed under intersection with regular languages. That's true. But are they closed under intersection with just themselves? So if I have two context-free languages here, is A intersect B context-free? So this is actually a homework question. So I want you to think about this more. But try to think of two. What is our favorite non-context-free language? Let's do that. 0 to the n, 1 to the n, 2 to the n. Well, suppose that could I have a context-free language where the number of zeros and ones is the same, but the number of twos can be arbitrary? Could I have a grammar that generates that language? Yeah. So I would do it, but I want you to think about it first. We can talk about it tomorrow. So think of that language. Same number of zeros and ones, and any number of twos at all. Now think of a different language. Same number of ones and twos, but an arbitrary number of zeros. I claim we can make a grammar for both of those. But what is their intersection? Yeah, same number of zeros and ones, and same number of ones and twos. But that's the same. They're the same number overall. So they're not closed under intersection. Okay? But I want you to think about it first. Any other questions? This is good. Okay, so what were we talking about last time? Yeah, Turing machines. So, and what in particular of Turing machines?
Multi-tape.
Yeah, multi-tape. And what did we show about multi-tape Turing machines?
Can we see that in one?
Right, yeah. So every single tape machine already is a multi-tape machine because you can just ignore the other tapes. But if we wanted to show that if we have a multi-tape machine, we can simulate it with a single one, then what we did was we just copied essentially the tape contents and separated them with delimiters and then made these big sweeping passes through the input. And then made changes as the case may be. The details are not really that important here. It's just that we can actually do it. So one thing that we showed with regular languages is that the non-deterministic model is the same thing as the deterministic model in terms of what they compute. They both compute the regular languages. We actually didn't talk about this because we're skipping that section. It turns out that the non-deterministic and deterministic models for context-free languages they're not the same. And if you're interested, I would highly recommend looking at that section because it's actually really, really interesting. But what about Turing machines? So is there a non-deterministic Turing machine? Is there a non-deterministic Turing machine where we could have multiple transitions on the same symbol that may do different things, and then we just choose one, like usual? Could there be a non-deterministic machine that has a language that a deterministic machine does not have? Is that possible? Well, is every deterministic machine already a non-deterministic one? Well, the non-deterministic model doesn't have to be non-deterministic. It can just be normally deterministic. So every Turing machine is already a non-deterministic Turing machine. So I forget where the comment comes from, but there's a comic somewhere where the instructor's at the blackboard and he's saying like, non-deterministic Turing machines are equivalent to deterministic Turing machines by Savage's theorem, which we may get to at some point. And then the students in the back with a thought bubble going, I just wanted to program video games. So, yeah. So this is clearly something that you would never be able to construct in real life, but this is getting somewhere. We will get to something that is actually really, really important that we will get to today, which is actually really interesting. But this is leading to it. So the question we would want to answer is, can we simulate a non-deterministic machine with a deterministic one? So could we take the non-deterministic model and then have a deterministic machine for the same language? What do you think the answer is? It turns out to be yes. You had a 50-50 chance. Might as well gamble. Let's go with yes. So why is it yes? Well, how did the DFA simulate the NFA at a high level? How did the DFA simulate the NFA? Well, what we did was we had a bunch of states that we might be in, and then we looked at everywhere we can go on the transition and then collapsed them all down to a single state in the DFA. Because we could be in any one of those states, and then we could have made any one of the choices out of any of those states. Well, could we do something similar here? Well, suppose that we have some configuration up here, some starting configuration. What is the configuration again? We talked about it last time. Yeah, it's the string of the tape contents, really. Well, if we have a non-deterministic machine, we might have choices, right? We don't have exactly one choice, we might have many. So maybe this starting config has, let's just say, 3 choices, and then the first one on the right, no, it's not the right, it's the left. It's really late already. The one on the left has 2 choices. Maybe the middle one had no choices after that, and then maybe the other one had 3 choices again. And then maybe this one has 2 choices, and then this one has a bunch of choices that go down, and then maybe this one has 2 choices. Yeah, so we can extend this as the case may be. So what this is called is the computation tree. So here's the thing. The non-deterministic machine could go down any one of these paths that it wants. If it says, oh, I have all these choices, I'm just going to pick one. It has all these choices to make. The deterministic machine does not have any choice at all. So what could the deterministic machine do? Well, the deterministic machine would have to search this entire tree, hopefully to find a configuration that has an accept state in it. Well, how would you explore this tree? Or in general, how would you explore a graph? If you're starting from a node, how would you explore a graph? Put your 310 hat on. Something FS. Depth first search. Would depth first search work here? You can tell by my tone it isn't. Why would it not work here? The problem might be, well, suppose that this configuration that I circled is the accept configuration, but we went down the left side of the tree and it went down infinitely far. Because trees can be infinite, we could have a computation that goes infinitely long. Maybe others don't go infinitely long, but one could. So depth first search is not the way to go here. What is a better way? Breadth first search. So why would breadth first search work in this case and not depth first search?
So
Yeah.
you find the answer before you get to the infinity range.
Yeah, well, here's the thing. Could there possibly be no accept configuration anywhere at all in this tree? Yeah, possibly. Or could it be that there's no reject configuration either? Yeah, it could possibly be. Is that a problem? Well, the non-deterministic machine would have never found it, so we wouldn't require the deterministic machine to ever find it either. But if there is an accept or reject configuration somewhere in this tree, it must be at a finite level, right? It can't be infinitely far down. So if I'm searching this tree level by level, well, could the tree grow infinitely far on the next level? So in other words, could there be a level, say this one right here, this second level, that has infinitely many children coming out of it? No, because there are a finite number of states. And so each level has a finite number of children. Well, that must mean I must explore a finite number of nodes to find this accept configuration if there is one. So all we need to do is at each iteration store the contents of each of these configurations. And that's all we do. Pretty interesting. So the fact that the Turing machine can actually store whole contents of tapes is why this method works. Why we can actually do this conversion from a non-deterministic machine to a deterministic one. Okay? So the details are absolutely not important at all. The high-level idea is important here. Because we're exploring a computation tree level by level, if the accept configuration is at some finite level, then we will find it in a finite number of steps because we can't have infinitely many children at each node. Okay? Yeah.
And this computation tree has both reject and accept.
Yeah, so it may be possible that the reject configurations are in red too. That's fine too.
So what happens when it goes in?
That's absolutely a fantastic point. So think about what non-determinism is. What does non-determinism say about choices that could be made? Yeah, so if there's one choice that will eventually lead me to accept, then I accept. So that must mean, well, I may encounter reject configurations along the way, as you suggested. So like, say these ones occur before the accept one that occurs further. Well, let's see what happens. So if I'm exploring this level by level, and suppose that there's no accept configuration whatsoever, there may be reject ones, but there's no accept ones, what will happen? I will run forever. Is that a problem? Do we accept the same string? We still do not accept the same string. Well, if there's an accept configuration, I definitely will find it. Well, if the non-deterministic machine never finds it, then it's going to keep making choices all the way down. Okay? So because as it has to make a choice at every single point, it can't just stop unless there's literally no choice to do. So it's going to keep making choices until it finds an accept config, but it will never find one. So it will run forever too. So in fact, the behavior is exactly the same. Thank you for bringing that up. Other questions? Yeah.
Instead of storing each row, couldn't you just, or like, why wouldn't you, I'm probably misunderstanding it, but why wouldn't you store like the path of the accepted state?
Yeah, you could. So that's how you would actually do it in practice. So what you would do is you would go down to the first level, then you would start at the top again because you got to keep that, and then work your way down from the first to the second level. Then you start again, go down to the third, go down to the fourth. So it would take even longer, but it can be done. Yeah, so you're right. That's how you would actually do it. But as I said, the details are just not necessary here. Other questions? Okay, so we're going to take a break in a second, but I want you to recognize something. Is there some kind of addition to a Turing machine that you can do that would get you to some language that a Turing machine can't recognize or decide? It seems like no matter what we throw at this problem, at these Turing machines, there's always a conversion back because we can actually store stuff on the actual tape. We can store an arbitrary amount of stuff and keep going back and forth and make changes along the way. So it seems like there is no way to show that there's some addition that can be made that makes normal Turing machines and ones with the addition different. And that intuition is actually right, and we'll talk about that after the break.